Okay, welcome to ninth lecture, stability of structure. So, let us briefly recapitulate what we have covered till now, especially for the second chapter. So, once we demonstrated the basic element of structural stability, and several classes of behavior, then we started with this real example by taking a simple structural system, that is column. We have we already learnt about the buckling of column in our undergraduate course, right. So, here in because this is stability little advanced. So, we have extended the discussion of buckling of column to the post buckling regime, and also several other issues we have introduced. For example, we have demonstrated first the amplification in displacement, or so amplification in displacement as well as moment, bending moment due to axial force, compression force, okay, in beam column, right. So, magnification factor for that depends on the ratio between the axial load divided by critical load, that ratio, right. Closer the axial compression to the critical compression, larger will be the amplification. Then we started the investigating the influence of shear force, shear deformation on the critical load, and we have seen that critical load for buckling actually that diminishes on incorporation of shear deformation. So, incorporation of this shear deformation is very important, okay, otherwise it lead to non-conservative design, right. So, the condition for which shear deformation will be significant, for example, in little deep beam and things, okay, deep thick plate and thick and the shear deformation must be included. And then we started with this finite deformation. We did not limit the deformation to be infinitely small, and that is what we referred that as elastica, the column undergoing finite deformation, right, under axial compression. And then we have seen that the governing equation can be expressed ultimately in terms of an elliptical integral of the first kind, and from there using some kind of approximation of the elliptical integral, we have demonstrated the symmetric bifurcation, symmetric stable bifurcation behavior, which we have observed in simple system, namely the rigid bar restrained with a rotational spring, and we have seen that this kind of thing is not imperfection sensitive, okay. And then we have also demonstrated that, well, I mean, it shows very little post critical strength, even for 30-degree rotation at the end, it can lead to only 3% increase in the in the load carrying capacity. So, for column we cannot rely on the post critical reserve, right. So, as soon as column buckle, it will not retain its capacity to load, it will basically deplete all the capacity of resisting axial compression, right. So, now and then we have also expressed lateral deflection as well as axial axial translation deflection using in terms of this quantity lambda, that is root p by ei, right, and also elliptical integral of the second kind, okay. Anyway, so now what we are going to start is once again we are going to discuss on buckling of column, but we are addressing a little advanced topic, right. So, what we are going to do now, we are going to describe torsional flexural buckling of column, torsional flexural buckling of column. Please note that till now whatever we have learned is basically the flexural buckling. Why? Because when it is going to out of plane deflection, it was through bending, we did not consider torsion. So, where this and mostly all of this hot rolled section, especially wide flange, they essentially buckle by flexural buckling only, okay. But there are sections which are asymmetric, okay, in which the CG, center of gravity, does not essentially coincide with the shear center. All of you know what is the shear center, right. Shear center is nothing but the point through which if the load is applied, then it does not produce any torsion, right. So, you know how to find out shear center for a section. If shear center and CG does not coincide, then and the bending will essentially be accompanied with what? Torsion, right. So, we are going to consider those kind of sections, okay. And in that case it will not allow it to only lose the stability by flexure, but torsion will also be combined. So, here what we are going to consider, because most of the civil engineering civil engineering system and even aerospace system, these are consisting of thin wall section, okay, or section which are not non-circular. So, we have learned about the torsion of the circular cross section, okay, and based on certain assumption, right. So, the assumption for circular section was that the plane section will remain plane, just like bending, here also for a shaft, circular cross section shaft, the plane section will remain plane, because there is no out of plane deformation, right. So, essentially the torque is resisted by the shear stresses, relative shear between the different sections, right, isn't it. So, so if you can recall that here was this kind of a shaft, right, and then if you can plot this shear stresses, distribution of shear stress. So, it will be linear, right, and then the formula was like T by J is equal to G into P by L, and of course, it was tau by R also, right, that was the thing, right. So, T is nothing but G J phi by L, and then if you want to write in terms of we can write d phi upon dx, right, d phi upon dz if we consider the longitudinal direction to be aligned with the z axis, right, if we consider this is aligned with the z axis. So, you see tau basically is proportional to R. So, it is increasing, and then please note that the stress. So, if you just consider a very small section here, so the stresses essentially it is something like this and something like this, right. On the free surface there will be no shear stresses, right. So, this, and then another assumption was also there, that any of this cross section when it is deforming, this remain on a line, okay. So, that basically it is as if it is under upon twisting when it is deforming under twist. So, it is essentially rotating right rigidly, okay, as if it is rotating rigidly. So, this section will remain like on a line, right, radial line, right. So, the problem is that these are all this was the torsion of circular section, but as soon as it is non-circular section, torsion of non-circular section, torsion of non-circular section, section, all this assumption is no more valid, right. For example, if you consider a rectangular section, into the rectangular section, right, then what will happen, if you have seen that you can either have a displacement formulation and you can have a stress formulation, So, then and if you can recall that the governing equation was like is equal to 0, right, stress function, right, Prandtl stress function formulation things, right. There are two alternate formulations. I am not going, and then you have solved the boundary value problem. We have seen that what happened, that plane section in the out of plane direction, in the z direction, plane section no more remain plane, rather there is warping. So, when it is subjected to some torsion, one of the quadrant is coming out, it is bulging out, another quadrant is going inside, another one is coming out, another is going inside, right. So, this is called warping, right, warping. So, warping of cross section is very important, warping of cross section for not cross section. This is very important. Then you have also find out the warping amplitude magnitude, right. So, be it rectangular, be it elliptical, whatever, right. So, then and but one thing is very important, that one thing is still is I think it is still valid, that shear stresses is varies basically. So, it is still with radial line, if you draw a radial line so it increases linearly, okay, right, isn't it. And at any point, if you see in any point you can draw a radial line, and the shear stresses here is basically proportional to this distance, right. So, warping is one which is unlike the non-circular cross section. In warping is extremely important. So, please note that what warping does, this warping and what we are, this warping induces the additional stresses, if this warping are prevented, if you prevent warping, so what we have learned, there will be two components, Saint-Venant torsion, right, Saint-Venant torsion, and there will be warping torsion. So, torsion, the torque will be resisted by two components, one is by shear stresses, another one is, see, whenever this warping is resisted, for example, you take a cross section and the warping you are preventing, okay, no autoplane, then there will, this will induce axial stresses in the fiber, right. If you prevent warping, that will induce axial stresses, right. So, in addition to shear stresses, there will be axial stresses also, right. So, the torsion will be resisted, total torsion torque will be resisted by one Saint-Venant component and another one is the warping torsion, right, two, isn't it. Now, so what we are going to consider here is mostly thin walled section. We are going to consider thin walled section. Thin walled section. Why? Because thin walled sections will be more susceptible to that. Here, okay. For example, and thin walled sections, for example, I section, or and then what we are going to consider mainly open section, not the closed section. Open section we are going to consider, because for the closed section, what happened is that for the closed section, the warping torsion, torsional constant is too high, okay, to have any significant warping. So, what now, as we have learned, we have find out Saint-Venant component of torsion for all rectangular section, elliptical section. For example, for an ellipse, for an elliptical section, if you can recall that, the same formula is varied. So, T will be, torque will be G J, G J, d phi upon dz, right, right. So, G is the shear modulus and J is the torsional constant, Saint-Venant torsional, Saint-Venant torsional constant, right, torsional constant or torsional constant, and d phi dz, phi is the twist, angle of twist, phi is the twist angle, angle of twist, and d phi dz is nothing but, if you want to define as theta, that is twist per unit length. So, J you have find out for various this is, for example, here it is pi a cube b cube divided by a square plus b square, something like this, right. This was the expression for the rectangular, for the elliptical section, and then for elliptical section, if it is subject to like this kind of torque, what will happen? This quadrant will go inside and this quadrant will come out, and then you will go inside, it will come out. So, bulging will happen, right. And then for rectangular section, if you can recall, for rectangular section, section, if we consider this is A and this is B, B, then J will be basically, some constant alpha, B into A cube. What is that B into A cube? Whatever is a smaller dimension that will come as cube, okay, and alpha is some constant. For different thing, alpha will be different, okay. So, these things, so you know how to find out Saint-Venant torsional constant for different section, that we have learned in mechanics course, right. And these are for the solid cross sections, but if you can recall that for thin walled section, now for the thin walled section, I don't know how we were these things were discussed in thin walled section. There are more general formulations, but let me, thin walled section J was, there can be two classifications, one is open, one is closed, open section, and another one is closed section. closed section. So, what is open section? Open section maybe is basically nothing but maybe something like this. This is open section. This is open section. I section is open section, right? Open section, and maybe this angle channel section is an open section because it is not closed, right? And what is closed section? Closed section is maybe what if if it is trapezoidal, like what we use in box girder, right? Something like this, and maybe this circular section, all these things you have learned or what in mechanics course? Thin wall section torsion. How this torsion? Did you find out? And for this thing, torsion was discussed there in the mechanics class or not? So you tell me what is the torsional constant for the open section? All of you have noted down this, right? This I am just briefly brushing up your torsion, non-circular section and thin wall section. Okay. So if you can recall for the open section, for the open J was nothing but summation of Bi Ti cube upon 3. Okay, where Ti is nothing but thickness. Ti is the thickness of individual section, and Bi is width or length, width of individual component. That means here if you consider this is a rectangular section. So this fellow, this is the width B1, this will be B1, this is T1, okay, T1. Then this is from here to here, this is B2, and then this is T2, okay, T2. Then this is B3, T3. So individual section you just sum them up, okay. So I is equal to 1 to number of component in the section. So it's open section, clear. Similarly for rectangular section, this is B1, T1, okay. Now for the closed section, closed one, J is nothing but 4 square divided by integration ds upon t. That means here it is 4 square divided by summation of summation of Si upon Ti. So T is equal to I to N. A square means A is nothing but the area that is of this section. You draw the central line, whatever the area that is closed by the central line, and T is this is the thickness T, and S is basically this length. Understand that 4 square divided by SI Ti. These are torsional constant, Saint Venant torsional constant, these are. Now what about warping? Warping constant I will come later. Please note that for the open section, this one is for the Saint Venant component, that means Saint Venant, that means the one contributed by shear, by which is registered by shear between the different cross section, okay, that was. Now for the warping torsion, for the open we will show you, there will be some warping constant will be there, some warping constant, I will tell you how to find it out, okay, some warping constant. But for the closed section, the warping constant is nearly 0. For closed it is nearly 0, it is means warping, it doesn't really occur basically, it's I mean warping is nearly 0. So we do not require, we can have the thing warping nearly 0, that means we do not warping nearly 0, that means you do not need to consider the warping constant, you understand, because the closed section hardly warp, okay, it is very rigid against warping, okay. But closed, the open section will warp, okay. So now, having said that, we will try to, I am just removing this part. I do not know how it was discussed, but if you can recall that there was, for the thin wall section, for the, thin wall, torsional and for the thin wall section, if you consider the texture bending and torsion theory, combined, bending, torsion, this is described by Vlasov theory, and there you will see that that there is some new concept introduced that is called by moment, moment of moment, by moment, and there is some element sectorial coordinate. I cannot go in details, but this is not simple stuff. By moment, sectorial coordinates, all these are there. Okay, it's not very similar. Just in analogy with the bending theory, they have developed these things. Okay, but we are not going. We are going to do it much simpler way, little ad hoc way. Okay, hope. Now, for any tube wall section, I am specifically mentioning to you. I am going to consider a section, maybe something like this, I section. I am going to consider an I section. This is an I section. So, here is my I section. So, here it is going, and then I am here, and then my coordinate systems I am choosing this, and of course, here you can see the shear center on this is symmetric, then x, this is x and shear center, and then CG is same right here. So, x and this fellow is y, and then the out of 10 direction is z, x, y, z. Okay. There are two flange and this is the wave. Okay. Now, and then I am there it is subjected to some torsion. Okay, or using torsion I can defining torsion T. Okay, torque T. Clear? So, now what happened is that so total torque is basically contributed to Saint Venant and T is warping, right? We know whatever for the Saint Venant, what is the expression? G J d beta by dz, right? That is the expression. J is the Saint Venant torsional constant and beta is the twist angle of twist, beta is the angle of twist, angle of So, beta angle of twist so this fellow is the way and we write it something like this so if it is like this here here, so when it is twisting it is twisting, it is something like this this something like this so it will be you see that it is twisted, right. So, I am just after twisting the section will look something like this. Okay. So, this is the angle and then this angle is essentially beta. Okay. Clear? So, d beta dz. Now, for the we do not know what will how to treat, because we are all familiar with the Saint Venant torsion, but we are not familiar with the warping torsion, right. So, let us see what we will do warping torsion. Warping torsion. Okay. So, now I am not going to to introduce you with the Vlasov theory by moment. I will mention what is by moment and sectorial coordinate. I am not going to do that. Okay. I am going to make it very simple. Okay. But it's those things are not in the present context. Okay. Because we are only concerned about the torsional-flexural buckling. Okay. That is what I am not going into there. So, now you tell me when this fellow is going to, if it is getting twisted. Okay. So, whenever it is subject to some kind of this kind of twist, right. So, what is going to happen? See, along with twist so this when you are applying this twist, what will happen, that this twist will essentially be accompanied by bending in the flange, right. So, when you are twisting it, maybe if this fellow, so if this fellow, this one, this cross section may bend like this, you see there, whatever will be the bending in this cross section, and the sense of bending here in this cross section will be different. You understand what I am trying to tell you, right? Because when it is basically twisted, it will be twisted. So, if this bends in this curvature, the bottom flange, will bend in the opposite curvature, right. So, what I am trying to mean is that here, let me draw it. Okay. If the top flange is I am considering that this is the along the length, okay, along the so if the bottom flange is going to deflect like this, is going to deflect like this, then the other one is going to deflect like you see that, you understand what I am saying to. So, this is maybe this is happening top flange, and this is the bending by the bottom flange, right. And that you can also understand why it is so, because you see that why it is so, because what is happening, it is trying to twist is clockwise. So, this fellow is moving in this direction, right, but at the fixed end it is trying to fix like this. So, it has to bend like this, it has to do like this. See, I am whatever I am drawing is little opposite, right, but you consider if it is bending like this, what is happening, this fellow is moving in this direction. So, when it is moving in this direction, this fellow is going to bend it like this, you see that, like this it is happening, and then this fellow is going to move it like this. So, it will, okay. So, you understand those. So, if we consider this one, now the contribution of the wave in the bending is negligible, right. It is the bending, the bending is essentially contributed by the flange. The wave is not going to bend, we can assume safely that this wave will remain in plane, right. Okay. So, now when it is bending, I am sure that there will be some hypothetical bending moment here, which is causing it to bend, right. So, this hypothetical bending moment I can define moment MF, hypothetical bending moment we can define MF, and these will be equal and opposite, right, MF and MF, right. So, MF is nothing but warping moment, MF is basically moment induced in the flange, moment induced in the flange by warping, right, or during warp, right. Now, that is why there. Now, when there is moment MF, right, there will also be associated shear, and associated shear we can define as Vf, right, Vf, and this Vf we can write Vf is nothing but minus dmf by dz shear force bending moment, this express, right. Okay. Please note that, right. So, if I want to define this Vf like this, okay. So, how will this Vf will occur, this Vf, here there will be Vf, V fix it, and here there will be Vf, you see that, because this shear is along the flange, along the section of the flange, this thin flange section along that, right, fine, okay. Now, you can clearly see that if these are the two shear which are developed, they will basically what? They will consist of a resulting both of this is going to cause a counteracting twist, TW is nothing but Vf into H. If we consider this depth of the flange to be H, then H into Vf will be nothing but some component of twist, and that twist is nothing but the warping contribute to the warping torsion. You understand that? Now, you may say that, sir, why it is also coming this direction, it is nothing basically, if it is externally applied in this direction, then it will be resulting. Okay. So, you do not worry about that. So, you understand how I am going to get, I am getting here the twisting component of the twisting, the warping torsion, torsion that is basically in action to counteract the the twisting, right. You see that. So, external torque whatever being applied is resisted by Sandvenon, and other words due to by the warping. The warping component is nothing but Vf, and when I am writing Vf, Vf is nothing but once again minus d Mf by dz into H, or you can, it is not essentially you can also write it is to be positive here, sorry. V is equal to dmdf for negative sign. See, if this negative sign come here, then of course, then m is equal to minus there, in one places it will be there depending on the choice of your coordinate, right. I am not going into those things right now, okay. Let it be like that, okay. Fine. Fine. So, now I am removing this one. What is H? You understand? H is nothing but the depth of the wave, okay. So, I am going to put it there, and then I will once again write. Now, what I will write, MF. Now, if MF I can write when E IF d2 u by dz2, can I write like this? Yes. What is E? Modulus elasticity. IF is what? If this flange is bending, that means the moment of second moment of area of this flange with respect to this axis, the axis which is aligned along the wave, right. So, that is IF. IF is nothing but second second area, moment of area, second moment of area with respect to this this axis, right. So, this is for the flange only, right. And what is d2u dz2? d2u dz2 is nothing but this. If this is deflecting, so this deflection is occurring like this. This is the bending because of this lateral deflection, right. And this lateral deflection is happening what? Along x direction. It is happening, this direction is nothing but x, and we are defining that there is displacement component along x it is u, along y it is v, right, and along z it will be w, okay, whatever. So, this is the displacement component, you see that. So, if that is so, then del to u del z to why z, because z is along the longitudinal axis. So, you understand, is that correct? All of you understood why E IF del to u del z to IF is nothing but the second moment of area of the flange, fine. So, please try to understand because that warping, because of warping what kind of differential moment, bending moment is shared by is developed in the flange, and then how it is resisting, and I am just using simple bending formula, I am neglecting shear, no shear difference. So, just to write this, clear. So, what I am going to do now, I am substituting over here. So, should I remove this? Should I remove this? I can remove this part at least, right? I can remove this part, and what I can write that TW is nothing but dmf by dz into H, and dmf by dz is minus EIF del 3 u by d z 3 into h, right? Now, you tell me what is u? U is nothing but what? U is what? U is this deflection, right? U. This u is what? This u or this u? This is u is what? U is nothing but what? Beta into h by 2. Beta into h by 2, because this angle is beta and this, this deflection beta into h by 2. So, what I will do here, minus E I f, and I am going to h, of course, beta will change, but h by 2 I will outside I will put h, and then d 3 beta dz 3, right. So, it is going to what, minus E I f h square by 2 d 3 beta d z 3. So, what I will write now here please see here, I will bring it once again. So, I am just going to T W is nothing but E I f by 2 h square d 3 beta d z 3, clear. So, here you please see that here is G j and I f h square by 2 I am going to define is capital lambda, okay, which is I f h square upon 2. This we are going to define as the see, this is Saint Venant torsional rigidity, right, Saint Venant torsional constant. Here we can define as to be warping constant, right. So, warping constant of the section, constant, and it depends of the section, So, IF is of course is the it depends on the flange dimension. H is nothing but the depth of the wave. IF h square by 2 is a constant for the cross section. It's just like moment of area, moment area, of course higher dimension, right, fourth order, right. So, I will just simplify it further, and the way I am going to do it, you see, is I am removing all these things now, and so I am writing G j d beta d z minus capital E lambda d 3 beta d z 3, that. So, total torsion, the torque is registered by Saint Venant and warping. This is Saint Venant torsion, which is registered by shear, and this warping is registered by axial force developed, this is by shear stress between the different cross section, which is there by axial stress in the fiber, axial stress in the of course, if it is restant in the fiber along the axial direction. Here now, and lambda, please capital lambda, so capital omega, I believe it is capital omega, right, I f h square by 2, this one is a things capital omega, this is capital omega is basically the warping constant, which is dependent on the section, okay. Now, here before I go later, here I will just try to tell you something. What happened is that, you see, when these two, so this what is happening is that when this fellow is subjected to this torque, this twist, then some differential this thing is happening, and then these two sections are subjected to bending. What really happens is that, see, this fellow is subjected to some bending moment, right, and this fellow is going to have some bending moment, right. So, here some bending is happening, here also some bending is happening, and they are in different, so moment in the flange, right, and there is some distance, okay. So, there is this bi moment, which is called bi moment, okay. you do not require to know this, but just to introduce. By moment is can be defined as ma multiplied by this h. This is called by moment. Okay. This is called by moment, and then because it is by moment, you see, that is why its dimension will be whatever the bending moment, and then there is another additional h. Okay. So, that is why you see that there is if h square by 2. So, it is not only related by, similarly by moment can be related to the if you just put it mf into h, this mf is what? Mf is nothing but minus e if y d2 u by dz2, right, into h, and then you have written that minus e if ah, and this u is nothing but h by 2 into beta, right. So, h by 2 into beta d2 beta dz2. Okay. So, minus e if h square by 2 d2 beta dz2. Do you see? See, we are having a similar expression of by moment. So, what we see that this, you see that b is nothing but, by moment is nothing but minus this is nothing but capital E omega d2 beta dz2. Do you see the same expression as when m is equal to minus ei d2 w dx2? You see that ei instead of I, this capital gamma is nothing but this, this is called I mean in literature this is called I omega, that means the torsion, the warping constant of the section. So, do you see the how by moment is related to the twist, you see, and there is the separate formalism is how to calculate. See, here we are doing it very simple way, okay, but you please note that if we want to take the contribution of the wave as well along with flange, then there are technique, there are theory, where you can kind of can find out the capital omega, and that is where those there are some coordinate system, those are defined as sectorial coordinate system. Okay. Sectorial coordinate is nothing but there will be a pole, I mean you can take that CS center to be, okay, and then the perpendicular distance from that thing to the center line of the sections. Okay. When you have to do over the whole along the center line of the whole section. Okay. And there is the sectorial coordinates will is nothing but the 2 into area which. So, for example, you consider a section like this, okay, and then from there, so you see that sectorial coordinate will. So, this is the area from here to here when you are moving 2 into this area will be some kind of sectorial coordinate. So, all these things are there, but you understand why we define by moment, because whenever this twisting is occurring, this warping is happening, there is some quantity which is moment of moment, you see that. So, that is why it is called by moment. Anyway, those things are not relevant here, but there are Vlasov theory you can learn, there are in depth, those are discussed in different book by Gerev and Weber and others. Okay. So, we reached here. Now, if you want to, we always followed the energy approach, right, for the same stability analysis. So, here if we want to write the energy for energy, strain energy rather, strain energy for Sane-Venant torsion, Sane-Venant and warping torsion, I do not require to derive it, but you can understand U is equal to Sane-Venant and U warping torsion warping. So, Sane-Venant will be what? You all know what is. So, integration real Gj. What is strain energy? Gj d beta dz square dz, it is same as the like axially loaded bar, right, AE, du dz square dz, right, that is you know how to derive this thing, right, I do not require to derive it, right, all of you know. And what about for the warping? Warping one will be what? Try to just it will be Gj by 2, there will be one Gj by 2, right, or half we have to take it out, right, half, right. And here also will be what? Plus half you have to take out E capital omega what? d2 beta z2 square dz. I am not deriving it, I mean you can do it, right, it is not a big deal. Half E capital omega d2 beta, right. Essentially you just substitute in the expression. So, E if by 2 d2u dz2 square, right. This is for individual flange. For individual flange it is like this. It should be multiplied by 2 because there are 2 flange and dz. Okay. And then you just simplify that and you will get it, right. Fine. So, when we derive the, now we are going to consider a, any section, any arbitrary section, and this arbitrary section we want to, we are going to consider some column. Okay. So, this is x, this is y, this is z, okay, and then there is this column is there, and this column is subjected to some axial force, axial force maybe P, okay, and this fellow has some in the x y, if you consider this is x and this is y, or there will be some, some cross section will be something like this, okay, and then it will have some. Please note that the CG, the CG of this x y we are considering as the shear center. This center is the C, is nothing but shear center, origin is shear center, and there is a reason for that. And this is the CG of the section, CG of the section, of the cross section, cross section. Why it is so? Because if we take the shear center to be the, so here in this origin is fixed at shear center. For the column, the origin is fixed at the shear center, whereas the CG of the cross section is at a different place. Okay. So, maybe, okay. So, from here to here it is x 0, and from here to here I am defining as y 0. So, x 0 and y 0 are the coordinate of the CG, x 0, y 0 are the coordinates of CG, coordinate of the CG, the cross section, CG of the cross section of the cross section, x 0, y 0, okay, and CG the origin with the origin at origin fixed at the shear center, fixed at the shear center, shear center. Why origin is fixed at the shear center? Because if we fix the origin at the shear center, then we can decompose the component into 3 component, because we will have then, because then, then there will be 3 component Tu, V and beta. U is the translation along x, deflection translation along x, and a translation along y, and B is the twist. You see, U, V and W, okay. This is U, this is V and this is W, okay. U, V and beta, beta is the twist. We do not have W because essentially we are concerned about the 2 deflection and 1 twist, rotation, right, of the section, cross section, right, that is what essential. So, here it is happening like this, but ultimately when it will deform, what will happen, these are, so from these, it might, it will go to a, you have noted it down, right. So, what will happen is that, that I will show it there, okay, I will show it there, right. So, what we can do at first, we can find out the strain energy U, okay, we can find out the strain energy, or we can do it later, let us first do the work done, okay, then we will go there. You see, let us consider, so consider that the column at both ends are restrained against twist, twist. So, please note that these are for the strain energy due to torsion, okay, but there will be strain energy due to bending also, right, because along U and V the bending will also be there, right, okay. So, along with that there will be also, other terms will be there, I will come there, restraint against twist and deflection, but are free but are free against warping. What does it mean? That means that Z is equal to 0 and Z is equal to L. At Z is equal to 0, U is equal to 0, V is equal to 0, beta is equal to 0. Here also at U is equal to 0, V is equal to 0, beta is equal to 0, right, because they are restrained, there is no deflection and it is restrained against twist, beta is equal to 0, right. But when it is restrained against rotation, when please MF is nothing but EIF d2 U dz2, right, and then this is nothing but minus EIF h by 2 d2 beta dz2, right. So, when it is restrained, when I am saying that it is restrained against not restrained against against warping. If it is not restrained against warping, that means MF must be 0, that is MF is 0, MF is 0. If MF is 0, then what? D2 beta dz2 is 0 at z is equal to 0 and at z is equal to L. You understand what I am trying to tell you? All of you understood, right, what I am trying to tell you, right? They are restrained against deflection. So, U0, E0, V0, V0 beta is equal to 0, restrained against twist, but they are not restrained against warping. So, if they are not restrained against warping, that means MF should be 0 at the end. If it is restrained, then there will be some MF. But so, D2 beta fine. Okay. Could you please tell why do I require this condition? Any differential equation, okay, whatever the highest derivative exists in the differential equation, the boundary condition must be specified, in terms of derivative which is one order lesser than that. the twisting torque was what? Gj d2 beta dt2 minus E capital gamma d3 beta dz3, right. So, one order let us mean it, one order lesser mean third order, it will be second order. Moreover, what is the higher order derivative here? d2 beta d beta dt, right. So, d2 beta dz2, okay, we can have some functions, okay, which can satisfy, by satisfying all these things we can assume some function and then we can substitute over there and then we can do the minimization, okay, fine. When we are assuming the that if this is the case, then we can assume that u and v and beta, we can assume psi 1 sin pi z by L, C2 sin pi z by L, C3 sin pi z by L, because this all satisfy that, right? Huh? Isn't it? All satisfy this, double differentiate, sine will be cosine, cosine will be sine, fine. Okay, so this we can assume, the way we assume that, we assume by satisfying the boundary conditions, right. And now the total strain energy will be strain energy bending and strain energy due to bending. So, strain energy due to bending will be half integration 0 to L E I. Please note that along d2u dz2 square. So, u means it is deflection along x, that means it will be moment of area will be with respect to y axis, right, and then plus half integration 0 to L E I x x d2v dz2 square dz. You understand why because when it is bending with respect to along the x, u is along x, right. So, it is deflecting along x, that means the moment of inertia will be with respect to, or moment of area will be with respect to y axis, and so, right. If it is deflecting along y, that means along the x axis, right. Clear? So, this is for the bending, this is for the warping, and this is for the set bend and torsion, all component, right. So, we are discussing torsional flexural buckling, that is what you have to consider all the component, okay. And so, now you take and substitute, you take this and substitute. So, you substitute in this, substitute. Take and substitute is not a big deal, it was basically you differentiate and substitute and then you integrate, and I told you that for all this problem you recall the integral, standard integral, integration 0 to L sine square pi z by L dz is equal to half and things like that, okay. So, I will write, may I write down the final expression? This integration is nothing, it is very simple, it's like it's a baby's job, right, okay. So, I am removing this and E will be final expression I am going to write, and E will be, let me write down, substituting this, it will be pi square by 4L L and then C1 square y square E I y by L square plus C2 square y square E Ix by L square plus C3 square Gj plus pi square E lambda Please note that we are getting expressions which are reminding us the expression for the critical load pi square EIL square. Okay, we will come there later, but these are basically, I mean, of course, you can see C1, C2, C3, and then when they are appearing in square, all this square term will be there. That's why C1 square, C2 square, C3 square is there, right? Now, for the bending, these two term, U and V, that will be two separate term. That's why pi square EIY by L square, pi square EIX by L square. These are because of these two term, and then the Saint Venant and then warping one. For the Saint Venant, GJ C3 square, and for the warping one, it is pi square E capital gamma by L square. Now, interesting thing to see is that, look, for the GJ Saint Venant part, there is no pi square by L square term is associated. Why it is so? Because see, in all other terms it is bending. See, when it is resisting to a twist, torque by warping, it is essentially, it involves what? Differential bending of the flanges. So that's what similar flexure rigidity terms are coming, E capital omega, right? But when it is Saint Venant torsion, it is more, it is analogous to what? Axially loaded bar. That's what in the strain energy expression it is Jj dBT dz square. All other are second order derivative, but here is first order derivative, right? So that's why it is only Gj. So dimensionless, dimension wise, these are all dimensionally consistent. Understand that, right? Okay. Now we are going to consider. So this is strain energy. Okay. Now we are going to consider work done, right? Work done. So how we will consider the work done? So this fellow, this column is there. Now we don't care about the cross section. We will consider. So here is this P, right? And here, whatever. So this fellow is going to now, it will come and it will come down, right? So it will basically deflect, some. So this is the deflection, right? So work done is P into delta, right? And then P into delta, and delta is what? U bar and V bar. These are nothing but what? The von Karman nonlinear term, right? Please note that here we are having x and y. So we are having deflection along x in component u, along y it is v. So von Karman nonlinear, both the component along x and v both must be considered. That's what I am taking del u bar del z square dz, yeah, right? Both. Okay. And then that should be multiplied by P, right, to have the work done, right, W. Fine. Now there is another thing. See, why I am putting U bar and V bar. U bar and V bar I am putting because you see that U, V and W are the what? U, V and W are the what? Here the deflection for the at the of the CG, right? That's what we have taken, right? But here what will happen, another thing will be come into picture, that you please note it down. So what will happen, the section is also undergoing twist. Because of twist, there will be some U and V. U and V will be modified. That's why U bar V bar. So there will be additional thing with U and V. So how that is? That I am just basically explaining to you. Okay. So here is the here I am here you consider here was the point, I am considering this was the point, right? This was the point. P, point P. Now, I mean, when it is being twisted, assuming that it is coming here, right. So, it is P dot, right, and of course, this angle is beta is, and it is very less. So, I mean, we can essentially replace the arc with this one, right. So, what I am going to do, and then this angle I am assuming as if this is so let me show it to you that what essentially is happening. Okay. So, you see when I am plotting what is the coordinate of my axis, this is the shear center is the my origin, right. So, I have this maybe this section here, I have this section here, right, and it has hit CG. So, from here this is CG, this is CG. So, this is x0 and from here to here this one is y0, right. Right. Now, from this CG it is going to some other another other point, so from here it is going somewhere here. Okay. So, what is that from here to here, what is that? This is u, and what is this from here to here? This is what? This is V. समझ रहे हो ना? See, from here I am amplifying, if this is infinitely small deformation, right, but I am amplifying the deformation. This CG is moving u, and then along this it is also moving this, but along with that it is also going through some twist, right. So, it is like anti-clock. So, basically so along with that this fellow is you see. So, along with that so this is, so you see that this is beta is happening here, you see that beta. So, what is happening? 3 stages of deformation. So, from here this fellow is then coming here because of translation, and then finally it is because of the rotation it is attaining this configuration. So, initially it was as x0 y0, here it was CG of the section, and this is shear center. So, from x0 y0 this CG is moving to x plus u and y plus v at this. In addition to that, there is twist with respect to z axis angle beta, right. So, this u and v are the pure translation, what initially. So, u and v are the pure translation component, but when there will be translation component contributed by beta also, that is what I am defining u bar v bar. You understand what is the difference between u v and u bar v bar? U bar v bar is nothing but the final component of the deformation y, which contribute both the pure component as well as component induced by this twist beta, right. So, this fellow was here and this fellow is going, and then this angle is beta, and what I am doing, I am going to drop this here I am going to drop this. So, from here to here I am assuming there is coordinate x0, okay, and then this fellow's coordinate is the y, basically not x0, say any point on the cross section. P is a point on the cross section, P is a typical point on the cross section, P is a typical point of the cross section, point on the section, the cross section of the section, right. So, this fellow, I mean, we are defining as this is x and this is y, and there will be a set of x and y, right. So, P is going to, so now you see that. So, from here what I am going to do, P is moving to P dot, and this is because of there is anticlock this rotation beta. Okay. Now, what I am going to do, I am dropping a perpendicular here, and I am also going to drop a perpendicular here, and then I am perpendicular here. Okay. This fellow is like this. So, this angle I am going to, this angle is alpha, this angle is alpha, this angle is also alpha, this angle is alpha, this angle is also alpha, right. This angle is alpha, this angle is alpha, this angle is also alpha. So, this I am I am measuring from this origin and to this distance, So, please note that here when I am rotating, it is basically this point, right. So, it is already translated, and then please note that this origin is nothing but this one. Okay. So, this fellow is going to be the origin here. Okay. Now, I am assuming that this rotation, this one, this radial line is nothing but what, r, okay, r. So, then I am putting this is r, this is r, okay. So, then what is this distance? This distance is nothing but what, beta into r. So, if that is beta into r, then what is happening? Because of this, what is this distance? What is this distance? This distance is nothing but, this one is nothing but what? Beta r, this angle is alpha, this is alpha, this is also alpha. So, beta r sin alpha. So, this one is nothing but beta r sin alpha, right. And if it is positive beta, anticlockwise beta, then this fellow is moving in the opposite direction, that means minus beta r sin alpha, right. So, what I can say, u bar is u minus beta r sin alpha, right. So, u bar along with u, whatever was the u, because of this rotation u will be reduced, but what about v? This v, and this is nothing but what, beta r cos alpha, this one, and this is in positive y direction, right. So, this is v plus beta r cosine of alpha, right. So, this is u minus beta. You tell me what is r sin alpha? R sin alpha is nothing but this is r, this sin alpha is what? This is x y. R sin alpha is nothing but y coordinate, and then r cos alpha is nothing but x. All of you understood what I am trying to do? The displacement component will be changed. There will be some component to the displacement, to the pure translation, u and v, because of the twist of the section, and that is what essentially I have defined. So, this u v is defined on each and every point on the cross section, right. So, this fellow, when we are going, this fellow is going to happen like this, right. So, I will tell you what else, this is of course p into, when we can write sigma dA, p will change, p is what? P is nothing but integration sigma dA over A. I will come there later, okay. Next class we will continue that, okay. Thank you very much for today's class.